All right, thanks everyone for coming. My name is Blake.
I'm Rylan.
And I'm Matt. This is our final design review for the Pettibone assembly lift. We'd like to start out by saying thank you to Pettibone, the NMU Engineering Technology faculty, as well as our peers for help along the way.
All right, to give you an overview of our project, I'd first like to introduce Pettibone. If you're unfamiliar with who they are, they're a heavy equipment manufacturer out of Baraga, Michigan. They make railway maintenance machines and other heavy lifting equipment, and they've tasked us with improving their method of installing this railway axle on the back of their machine. And the machine that you see up here is called the Speed Swing, and this railway axle they've named the High Rail. And the current method is a little inefficient and unsafe to their standards. You can see pry bars and overhead gantries and things moving the axle around. So we've been tasked with improving that. So here's the design overview. We've named this Alpha. We initially introduced two designs to Pettibone for them to choose from. We've named this one Alpha. The second one was respectively Beta. And this one was a little simpler, more time, or easier to build in a shorter period of time, basically. And they're using forklifts to move it around their facility. You can see the forklift tubes there pointed out. So moving it around the plant and then raising it and lowering it into their machine, they're using a forklift. Some other notable features on here, we have removable supports on the corners for when they're actually transporting this around their plant. The forklifts kind of bounce up and down a little bit, and those supports just kind of help with shock loading and things of that nature. And then the uprights on the top, if you can see those in front of the axle there, if you can't, you could probably see them up here. It makes it a little easier for them to lower this axle onto our frame here. And when the axle's on there, they can then put those removable uprights in there to secure it in place a little bit better. And then some changes that we did make after testing initially with Pettibone. We shortened the legs on the device just a little bit, 3 inches, because it was a little bit difficult to slide it underneath the back side of the Speed Swing machine. So we shortened the legs a little bit. We've added skid plates to the bottom so it slides on the concrete floor a little bit easier and distributes the load better. And then we've also added some eyelets to the upper frame so that if they want to add additional straps, ratchet straps, or things like that to secure it in place when moving, they've got those on there. And then our project status here, this is just a little schedule breakdown of where we're at. Starting with January and up until now, we've completely finished building our device, and it is ready for Pettibone to begin testing and using and making improvements on.
The design process for our Alpha fixture started with a trip to Pettibone. We met with the engineering staff and some of the production staff. They gave us a tour around the plant, and then we went over to where they install the high rail onto the Speed Swing machine. They have the Speed Swing machine up on some jacks, so we took measurements of the height and some of the space we have around it on the production floor, just to make sure that whatever we designed would fit within that space. After that trip, we were back here. We did a objective tree, pairwise comparison, a morphological chart, and then a decision matrix, and those are all different charts and tables that help narrow in characteristics and features that we want to focus on for our design. On the right side of the screen, you can see our pairwise comparison. We have some characteristics there that we were thinking of focusing on, and safety ended up being the most important. This makes sense because the project is mostly centered around making the process of installing the high rail axle safer for the manufacturing and assembly team. Once we knew what features and characteristics we wanted to focus on, each of us did a little hand sketch of a proposed idea, and then we used SOLIDWORKS 3D modeling to flesh those ideas out into a CAD model. We then met, compared pros and cons for each design, and came out with one design that we decided to move forward with that was sort of a mix of all of ours. We then started improving that. We presented it to staff here for the preliminary design review, where we got some feedback so we could make some design changes. And then we continued working on that throughout the rest of the semester. We used finite element analysis, which is a computer simulation where you can apply loads and it'll show you different stresses within the structure to determine if it was suitable. And then this is a prototype, and we did do a little bit of a prototyping process. We finished our initial build, tested it, had to change some things like Blake had mentioned, went back, did more testing, and in the future, it can be developed upon to make it more efficient and maybe even safer. This is a relatively low-risk project. Risk mitigation consisted mainly of verifying our FEA with hand calculations to make sure that they were accurate and that the structure would be suitable to hold the load. We also got feedback from faculty and from the staff at Pettibone. There were some changes and things they wanted to add. The big one was the supports that will reduce stress a lot in the upper frame when being transported. We didn't really have any large governing standards when we were designing this. It's a pretty simple installation fixture. It's not really being sold to anyone, but it did fall underneath some OSHA requirements. It's being moved with a forklift, but the tilt mechanism is done manually, so we had to make sure that the force required to raise or, well, tilt the tilt frame was less than 45 pounds. For engineering, the general structure, we kind of decided on 2-inch by 2-inch A36 steel square tubing. It's a relatively common size, and A36 steel is pretty common for structural material. And we picked that based off of some past experience that we've all had. We ran our finite element analysis on that. We ran those with an equivalent load of 2,500 pounds. At the time, we didn't have an exact weight for the high rail. CAD told us it was somewhere around 2,000, but since we were targeting a factor of safety of 2, we wanted to make sure that we had a little bit of extra room there. And then we targeted a factor of safety of 2, which means that stress at any given point in the frame needs to be less than half of the yield stress, so there's no permanent deformation of the structure when loaded. And everything fell above the factor of safety of 2, but you can see some high stress areas. When we were designing these, those high stress areas had a factor of safety below 2, so we had to do some design changes with like wall thickness of the steel tubing, and then we also added on those small plates between the hinges and the tilt frame that are being pointed to kind of add a little bit more rigidity in the middle there. The lead screw mechanism took some engineering as well. All the machined components that we were manufacturing, we tested with FEA, and every purchased component was rated for the load that we expected it to see. We also had to calculate the load that was going through the lead screw and then the torque that was going to be needed to turn the lead screw. And that was done with a lever arm, figuring out where half of the weight of the axle would sit on there, and then the distance from the hinge to the lead screw. And then some real life results that matched our FEA. The tilt frame and the lower frame both experienced some elastic deformation during testing. We put the axle on, the tilt frame kind of bowed down, and then the base frame kind of bowed up. It was less than a 1/16 of an inch, but it was still there, and that's something that we expected to see based off of our FEA. Something that was a little unexpected is that the lead screw ended up being a lot easier to turn than we'd calculated, and thinking about it, it really makes sense because half of the weight is on either side of the hinge, and it sort of cancels itself out. So the lead screw was really only overcoming frictional forces and maybe any binding in the lead screw. Some fabrication and assembly highlights were the CNC components. They estimated about 22 hours of just machine time, plus time for setup and getting material ready. We had 26 machined parts. Not all of them were fully machined, like the hinges were. Most of them were just little holes that were drilled or milled. The lead screw mechanism was a good highlight. It took some thinking to get that working properly and how we wanted it to, and to make sure it didn't interfere with the axle since it sits directly above it, or didn't make it difficult to use at all. Welding the frames took a fair bit of time. The upper frame had about 10 feet of weld, and then the lower frame had that, if not more. And then there was also some miscellaneous welding on the supports. It was also difficult to fixture the large weldments. We don't have necessarily the most ideal setup for that. So we did at one point have to cut and re-weld the base to fix some warpage, but we got it figured out and everything sits pretty well now. And then we got our first complete assembly done after we had everything else manufactured. It took less than an hour to put it together. There's just the tilt frame goes on, pins go in, and then the lead screw assembly goes on, and that's kind of it. And I'll hand it off to Matt.
So to go over some key results that we had, we completed our alpha build on March 29th. That day, we just kind of tested the function of our product, making sure there was no binding up in the hinges or the lead screw mechanism. Then we also had 4 of our peers stand on top and then kind of make sure there was no binding as well with the load on it. We had a second day of testing on April 2nd. That is when we verified that we needed to remove 3 inches off the legs to kind of give us some more clearance. And then a final day of testing on April 9th, when we, testing that day took way less time with that clearance added. And yeah, our product did what we were looking for it to do and checked all the boxes. And like any device, there is room for improvement, and this is easily something that can be modified in the future. So as a business case, Pettibone Traverse Lift came to us with a problem that they were looking for a solution, and we came up with some designs, kind of found what we thought would be a good solution. And with our design, you know, we can use this, or they can use this to assemble the high rail as well as install it. So rather than having them install it in 2 separate pieces, they can do it all at once, which kind of, you know, mitigates the risk of them having to lay underneath it during install. The hardest part with the install is kind of aligning that main pin that goes through the frame. And that's kind of going to be there no matter what. But I think with practice, it'll kind of become a more smoother transition. And then coming down to cost breakdown, it was roughly $1,200 in raw material. We estimated shipping of those products to be around $500. And for labor, we have an estimate of $4,000. That's 200 hours, and then 4 people at $20 an hour. Our design did what we were looking for it to do. It is robust and safe. And as far as performance, it works well. The hardest part is just aligning that pin. So to summarize where we're at with this, we were to develop an assembly device that can lift and tilt a heavy equipment axle onto a frame. It needs to be safe, effective, and user-friendly. Our design process, kind of getting the initial rundown of what the issue was, how we needed to get that axle under that frame. Kind of some constraints we had for it: effective, safe, low cost, compact. And then at the top right, kind of our final design for that solution. Some build highlights include fixturing to mitigate the risk of warpage during welding, our machined hinges, and then at the very end, our painted product. And yeah, it performed as we wanted it to. Any questions? They like it.
If I may, we need to talk into the mic so the live stream captures the questions. And also speakers, please talk into the mic so that it gets captured by live stream. All right. Admin note aside, please ask again.
Okay. What was the response from Pettibone upon your summary?
They do like it. It does exactly what they were hoping for it to do. And as I stated earlier, it is a device that can be improved upon in the future.
Could you expand on what those improvements could be or how you could have done things differently?
Yeah. So some improvements could be adding like caster wheels on the legs, just so it's easier to maneuver around without a forklift if they needed to position it just right for that pin alignment before it is raised up into the frame. Also, just a way to position it to the frame so it kind of goes in the same way every time.
Any more questions? All right. Well, nice job. Give another round of applause. All right, and our next group will begin at 1:20, and that is, the clay pigeon thrower. That's Jackson, Eric, and Colin. If you'd like to actually grade these, we do have a few more sheets, so if anyone is interested, I can get you some sheets while we are here. Students, I have a second sheet. Do we have any more of those student sheets, Leaf? We have a lot of the student sheets, so students, just some peer evals, what they do well, what they could learn from or improve on. How you doing? Good, good. You excited? You guys parents, or are you? Who's your kid? Oh, I see. Okay. You want a grade? I like it. You'll probably be the harshest one. Yeah, a lot of work. So thank you for coming, parents, well-wishers, friends, students who will be taking this class next semester. Pay attention. A good question to ask for you students who will take this next semester is, what lesson did you learn, right? And they will all tell you something different, but I think the spirit of the response will be something to the effect of, we should have started sooner. So just hear that every time. That's okay by me. All right, what time is it? Anybody, no joke? No, I'm teasing. I was tap dancing here. We need to ask more questions next time, okay? More questions. All right. Yeah, 1318, 1319. That's the appropriate response. 1319. Oh, you got the 13 there. Well done.
Yeah. Hello, everybody. We'd like to welcome you to our MET 431 Senior Project Design Review presentation. Our product is the Icarus Clay Pigeon Trap Thrower. I'm Colin Holton.
I'm Eric Atlamaki.
And I'm Jackson Bowers.
The first thing we want to hop in today with you guys today is our project overview. So the first thing, some background on our project. There's three key things we wanted to take away from the market. The cost effectiveness of the furthest left, the randomness of the second one, and the rabbit throwing style of the third. We implemented all three of these into our design, and we coined it Icarus.
On to our design overview. So a little bit of background on how our product works. There's four main mechanisms that all integrate and work together, those being the throwing, the loading, our pitch control or randomization, as well as our rabbit mode. So to start off, how our throwing mechanism works is we have two gears, as you can see. The one on the right is connected to the motor. The one on the left interfaces with the main shaft. These two are connected by a chain. So as the gear spins around these, or as the motor spins around these gears, the interface, which we call the paw, basically occurs. So the paw on the gear pushes against the paw on the main shaft, and up until about the 12 o'clock position, a spring is being pulled apart down here. You can kind of see that on the bottom. So it's being extended, and then right about at that 12 o'clock position, the main shaft is able to swing freely counterclockwise, and that's when the spring compresses and accelerates the main shaft, which our throwing arm is connected to.
So that shaft that Jackson was just talking about is attached at the very top to our cam cap, which is called out right here. That cam cap rotates around and pushes this device right here forward, which then in turn pushes our clay brake system up against the clays, not allowing any clays to fall in. At the very top here, you can slightly see right there is our clay brake slide. So that sits in there and the clay just drops in on there and stays on there while the throwing mechanism is out. And as soon as that clay mechanism starts, or that throwing mechanism comes back around and in, it drops that clay in, the clay brake releases, and that slide comes out, catches the next clay, and then the clay brake slides back across and locks it in place so no other clay can fall in.
So now I'm going to talk about some of the design changes that were made. On the left-hand side, figure 6, that was our original design from the fall semester. And on the right-hand side, figure 7, that's our current design. We had 3 big changes. You can't see it here, but inside of this frame here, there was a yaw motor, and what this was going to do was rotate the pigeon left and right, or the thrower left and right. And then our next change was the move of the pitch motor. So this moved to the back side on the new drawing, and we had to do this because our main motor came in, and we had to frame it a special way, and yes, we had to move it to cut for that. So here's some other changes we made. In figure 8, this is a 3D printed chain tensioner we made. So we had some issues with the chain skipping links during some of our automated testing, so we developed this to help mitigate that. In figure 10 at the bottom, we incorporated these L brackets, and the main purpose here is for easy disassembly. Originally we had this as welded, but doing this allowed us to take it apart way easier. I'll turn it to Jackson.
Some more design overview changes. On the left side, you can see our spring arm. It was originally welded to our main shaft. We decided to go away with that and incorporate a spline and hub configuration. This way we could change the angle that the spring arm was at, and we could change the timing of the throwing. After some testing, we needed to get a heavier duty spring, but instead of doing that, we just lengthened the arm of the spring arm. That way we could extend and compress the spring more. Here we have the circuitry for our stepper motor. We're controlling everything with an Arduino Uno, as well as a TB600 stepper driver. On the bottom right, you can see the circuitry for a debounce circuit. And then along with that, we have 2 limit switches that allow us to control how much pitch angle that we want. Here we have the gear motor circuitry. Again, we're using an Arduino Uno. Here we have a solid state relay that controls the motor, and then we also have an on-off switch and a foot switch that sends a time pulse to the motor to spin it for 1 revolution. Some of the highlights of our design overview is that we didn't have any major setbacks in terms of design change, so we didn't need a major overhaul. There were a lot of little ones though. The majority of our parts were CNC'd, so we got to save money there. And then we had no problem sourcing material thanks to Kale. Some of the challenges, obviously time, machining and programming, testing, and implementing design changes took up a vast majority of our time. We're all MET students, so we had to kind of brush off our electrical knowledge and learn Arduino as well as wiring and programming. And then finally, we started our design off in metric when everything in the lab is imperial, so we kind of had to convert everything over.
So now I'm going to talk about our current project status. So at the top here in figure 16, that's our original schedule that we set out in the fall. And then at the bottom, figure 17, that's our schedule that we followed, or the dates that we hit. So as you can see in the red on the bottom, we got hung up on our throwing tests. We really couldn't get the throwing arm to throw it like we really intended, so that really pushed back the secondary processes that we wanted to achieve.
So now hopping into our design process. So we utilized some tools that we learned in our senior projects this year. On the top there is that Gantt chart, which Eric was just talking about, which kept us on track for the most part. On the bottom left and on the bottom right are our decision matrix and our morphological chart. They both helped us choose our different parts of the machine that we wanted to add and implement, and allowed us to value what would be the most important and take those out. And as you know, starting any project, there's always risks. And the best thing to do to that is mitigate those risks. And we found time management, frequent testing, avoiding potential setbacks and having a solution for those whenever they arise, selecting proper material, and having safety protocols greatly mitigated any of those risks that we faced.
So on to fabrication and assembly. So a vast majority of our parts were CNC'd. We used a program called Mastercam that basically takes our 3D models and automates the G-code. So that saved us a lot of time. And then everything else that was aluminum or steel that we didn't CNC, we welded together. Here's me TIG welding some in aluminum. Materials used, primarily aluminum for its lightweight. Again, we wanted something that was portable, so aluminum's a thing to do. For heavier duty applications, like the gear shown on the bottom left middle picture, we use steel. We also did a lot of 3D printing. So on the top right, we have the limit switch housings for our limit switches. Those are using PLA filament. And for heavier duty applications that we still wanted to 3D print, we use PETG.
So with a lot of those changes that we made, we saved a bunch of money. On the left-hand side is the original price from the fall, which is roughly $1,412. The yellow highlighted in both of those are things that on the left is what we figured we could manufacture, and then on the right is what we actually manufactured. In the second semester here, we cut our price down to roughly $933. This was greatly reduced by simply removing that yaw motor that Eric was talking about, which would have costed us $405. All the red are on the right is where we saved money on. A lot of it came in the fact of having stuff on hand in the shop or having it personally at our houses.
Now I'm going to talk about some of the key results we found. So in this table here, you can see we have our target values that we set in the fall, which were compared to the actual. So for speed, we wanted 38 miles per hour, but we didn't really have a good way to measure that. So we don't have them there. For distance, we wanted to hit 180 feet, but our best throw we measured out was 45 feet. So we missed that. And then for cost, we went over by $300 for what we expected. Weight, we were down 6 pounds, which is actually a win. And loading time, we had inconsistent loading tests, so we had a hard time really coming up with a set value for that loading time. Our footprint, it grew by like roughly 25%. And then our spring ended up growing 4 times as large as what we thought we needed in the fall. So here's a picture from our throwing test. So we did this in 2 separate ways. The first way is manual. So to do that, we just manually spun around the throwing arm and let it fly. The first time we did this, it did not go as far as we wanted. So to improve this, we upgraded our spring and still wasn't throwing as far. Then the next upgrade we made, which you saw earlier in the spring arm, actually pulled our spring farther back, and that's how we achieved our farthest throw of 45 feet. And then the second way we did this test was actually using the automated part, which was using the chain and the sprockets. And in the next slide, you're gonna see a video of the chain skipping the teeth. And from doing this test a few times, we ended up with a fractured weld, which you'll also see. So here's the video. So you could really see those jumping around. And here's a picture of the fractured weld we had. This occurred in the bottom of the housing where our pitch is actually being applied. To fix this, we cut deeper grooves, and that allowed us to have a deeper weld penetration, and we didn't have any issues since that.
So on to our pitch control test. Again, we're using a stepper motor, and in order to control that, you need a stepper driver. For some reason, the manufacturer's website didn't have compatible drivers listed, so we had to kind of tinker around and find one that worked. Eventually, we found one. It would rotate the motor, but our limit switches wouldn't activate. After consulting Professor Pozega, she recommended implementing a debounce circuit. So after that was done, everything worked as intended until we did our final assembly with everything, including the full stack of clays and the resting position. If you look at our assembly, the arm sticks out, so that adds a bunch of extra weight out there. Ended up being too much for the brake to hold, so when the motor's not active, it'll start to like tilt down. However, when the motor is running, it'll still properly function. And then finally, we have our loading test. So again, we did a manual and an automatic style. Manual one just involved rotating the cam cap on the right by hand. And we started off with 2 clays. rotated the cap, and it would feed. It wasn't super consistent, and we decided to just step it up. So we did 3, 4, 5, and everything above 2 would pretty much jam the brake slide underneath and basically jam up the whole system. We still decided to do an automated test just to see what would happen, but nothing changed. And then finally, what we would have done was a rabbit mode. However, you saw our Gantt charts earlier. A lot of our time was spent working on the throwing arm, so early on we decided to just cut this out, and we're not going to test for rabbit mode. That being said, we still designed and manufactured everything to still do it, so if we changed our mind and wanted to do it in the future, it'll still be available.
So now hopping into the business side of this. Currently on the market, a lot of the commercial throwers are going to be systematically throwing clays, either be standard or rabbit and not have either both. And they're typically pretty expensive. That's where Icarus comes in. Typically we'd have randomized throwing, both styles, and be cost effective. On figure 31 on the bottom left, the companies in the dark blue are going to be running you roughly $2,000 to $3,000 for one of those clay throwers. And as you get out from that dark blue color, the prices get cheaper, but so does the quality of the work. So we want to be right there in between the contenders and the competitors with our work and still have the good quality that we will design. And figure 32 is the future market expected in the United States and around the world. Currently, the United States holds about 50% of the market for clay throwers, and a large portion of it is automatic compared to the manual style. So this brings us into our conclusion. Although we didn't hit our desired testing parameters, we learned a lot of experiences in the problem solving and troubleshooting, whether it be observing current and future problems that may occur, making quick decisions, executing the fix promptly, and retesting until we get it correct.
So now I'm going to talk about some of the lessons we learned. So in general, building and testing early is super critical for a project like this. You have to account for unforeseen circumstances, such as we had snow days, maybe a down machine, or a professor being out you were looking to talk to. Don't spread yourself too thin, and build your critical features first. So for us, that would have been really focusing on the throwing arm, getting that out there. More specifically, with like tight tolerance mates and things like that, there's really no room for play. We found that out the hard way. Stability for a project like this is super important. When you're transmitting a high torque like that, the bottom wants to move a lot. And also 3D printing for us was a really big time.
So on to future development. If we were to progress with this project further, or if a group wanted to take over this coming year, we'd first and foremost work on getting a properly functioning throwing arm. From there, we'd create a working feeding mechanism, as well as refine the motor to upper assembly, and finally try and simplify the design for ease of manufacturing and assembly. Looking back, we think we could have taken this project in a different direction. Instead of manufacturing everything from the ground up, like the throwing arm and the feeding mechanism, we could have looked towards getting something that was already out on the market, like an already made clay thrower, and developing a kit that would basically automate it. This way we would spend a lot less time trying to get down the simple stuff that already exists, like the throwing mechanism and the feeding mechanism. We could spend more time on doing the automated side that we kind of originally wanted to do with our project. Big thank you to the entire engineering faculty, as well as those listed up here especially, as well as Superior Extrusion and the Sump Pump Group. Any questions?
So you guys said that you had a problem with the chain jumping and skipping.
Yeah.
So do you guys think that was from the gear design, or do you think that was because of the lack of tension on the chain itself?
At first we did think it was the lack of tension. However, after doing a couple of tests after designing the tensioner, it seems like it might have been the gear. We did CNC the gear, so we didn't buy that, so it could have been any little variable in there. So we weren't exactly sure, but it seems like it can be the gear.
Just curious, you guys had one of your items up there that you posted on Instagram about your progress and everything.
Correct.
What kind of feedback have you gotten?
A lot of good support in the comments. Other than that, not too much. We just kind of, did our posts or our weekly updates with stuff like that and just feature posts. So, yeah.
What was the reasoning behind manufacturing the gear from scratch as opposed to buying a gear or sprocket? Sorry.
It was primarily the save cost. Again, before we started the project, we didn't really realize how expensive motors were, so that kind of took away a lot of our intention for buying like things like gears. The ones that we spec'd out for our design were, I think, $60 a piece. So trying to avoid spending $120, we just decided to make them in-house.
So you guys were talking about the throwing arms or maybe going to a kit option, right? So would you say looking at other throwers or looking at throw mechanisms as part of the research in the beginning would have affected, not just starting a different route, but would you have changed your design earlier, going more research?
Can you rephrase it?
So like, it looks like you're trying to do the throwing arm from scratch and you're not getting the results that you want. If you had researched other throwing mechanisms, do you feel like you'd have gotten the throwing mechanism where you wanted it better?
I think so, but I think we also intended, because we were set on doing everything from scratch, we wanted to differentiate.
Yeah.
We're trying to be different.
Yeah.
So, yeah, we decided to try and do a different route and see how that worked. Didn't really work out, so.
Yeah. Added challenges, yeah.
Correct.
Yeah.
Was any engineering analysis done up front, like a dynamics, rotational velocity, spring rate analysis done to try to estimate what the original, like, departing velocity might be of the clay pigeon?
Yeah, we did some hand calculations for that. I can't remember exactly what we set out for everything, but other than that, we did a lot of FEA for all of our 3D printed stuff. But yeah, something must have went awry in the spring tensioning one because it was significantly more than what we intended.
Any more questions?
Looking at a chain, did you think of a different device besides a chain, like a belt and a pulley system, to attach a pulley to the gear shaft?
I don't think we specifically went over like a pulley system. I think that would be viable. One other kind of design that we were thinking of is just a direct drive. So instead of having a chain, we would just have the motor sitting right under the main shaft and basically spin it that way. That way we would minimize losses through the chain and the gears. We didn't do that because we'd have so much weight from that motor hanging out that we'd have to get an even heavier duty motor in the back in order to balance that weight out.
So for each group, please stick around your displays when this is all over. If you have further questions, they'll be around to show you all the neat features of their designs. But one last round of applause. All right, so we now have Justin, Harrison, and Jim coming on down. All right. And start when you are ready.
Good afternoon, everyone. We are the Auxiliary Sump Pump System Group. My name is Harrison Klossner.
I'm Jim Turner. And I'm Justin Musoff.
As you may have noticed, we had a small QR code symbol on our first introductory slide, and the purpose for that is because with this product development, we've also developed an instruction manual. We put this QR code up for you guys if you would like to follow along with our instruction manual, as it does provide a lot of technical information on how our system operates. We will be covering a lot of the topics in the slide, but if you guys wish to dig into it a little bit further, this is just a nice little tool for you guys to kind of follow along with. And if you do miss it on this slide, it will be in the next few slides for you guys to scan as well.
So the project overview. What is our product? Our product is a control system for sub pumps. Essentially, what it does is it runs 3 pumps independently of each other. We actively monitor water level inside the sump. We chose this project because we were told we could reinvent the wheel, and all 3 of us have electrical backgrounds and experiences, and so we figured this would be a good project for us to do. The motivation for this project was flooding is costly both emotionally and financially, and we aim to go and solve that problem and make sure it never happens again.
So some of the key highlights of our final product, as Jim said, we developed a control system that's designed to operate several different pumps off of one enclosure. There are, as I said, a couple of different special features that we wanted to kind of point out to you guys. And again, the QR code is in the bottom of the screen. If you guys would like to read more on some of these special features, feel free to do so. But one of the special features of this system is that it has an active water level monitoring system in it. And this is done through the use of an ultrasonic sensor. And the ultrasonic sensor takes an information that's entered into the keypad by the homeowner or the user, and it's designed to turn on the pumps at different levels. Another one of the special features that makes our product very unique is the use of indicator lights. You can kind of see on our product back there, there are several lights mounted on the front of the panel, and each one of these lights comes with a tag. And so the tags are designed to kind of describe to the user what error has occurred with the enclosure, because as we wanted to really make this system as user-friendly as possible. A real big one is our auxiliary power system. This one really kind of gives our system its name. We came up with an auxiliary power system with a couple of deep cycle batteries. We wanted to use deep cycle batteries because they are able to lose more charge from them, but also be charged than the normal lead acid type of battery. And last but not least, we have user-friendly LCD and data entry systems. So as I kind of mentioned earlier with the ultrasonic sensor, this is kind of involved so that the homeowner, the user, is able to enter a water level into the LCD display, and that ultrasonic sensor will go and look for that water level that they entered. A crosswalk of our prototypes versus what we actually achieved. So this is what we promised in other presentations versus what we actually achieved in building it. We actually were able to adhere to everything that we had promised with the exception of one thing. Right now our current prototype is only operating with one ultrasonic sensor, but in our previous presentations we promised that there would be 2.
So the status of our project, it currently is entirely done, it has the ability to turn on all of these separate pumps at the correct water levels that it is set. It has the ability to run off both the wall power as well as DC battery for in case wall power is lost for whatever reason, such as a power outage within your home. So for project management, we started building the hardware in late February and early March and have continued to work on it up until this very week. Software I started in the late stages of February as well as the early stages of March, and that was only recently finished this week. So for the amount of time we spent each week on this project, it went from starting at 2 to 4 hours a week up to 6 to 10 hours a day. And then for the tools we have used in this project for time management and project management have been primarily the Microsoft and Google suites as the way of transmitting information, whether it be new documents, updates on code, updates on where the project is at in general, all sorts of things like this.
So for the engineering tools used in our project, obviously you got to start somewhere. We started with the design. So we used AutoCAD to go and draw everything up. We drew the enclosure, the interiors, and essentially this made sure that all of our components were going to fit together nicely. We then moved on to Multisim. For those of you who don't know what Multisim is, it's an electronic simulation software. We were able to use that to make sure all of our components were going to jive well with each other. Thankfully they did, so we didn't have to go and redesign. Arduino IDE, that's the program used to actually program the microcontroller, so that was used extensively. As Justin said, Microsoft and Google Suite, this project was very complex, so there was a lot of communication and updates that needed to happen. So we utilized those two to make sure that everybody was informed with what was going on. And then we used multimeters for continuity tests, current tests, voltage checks, all that kind of stuff. In terms of risk management, this product didn't really have a whole lot of risks associated. Obviously, there were some hazardous voltages inside the panel. Thankfully, there wasn't any major incidents with that. We are using a GFCI protected power cord that's similar to what you'd find in the bathroom, so there's no chance of getting shocked or electrocuted. And we did include current limiting devices in the form of circuit breakers inside the enclosure. Governing standards and applicable codes, there's not really anything that's specifically pertaining to our project. Plumbing Code Chapter 11, that goes and talks about where you can and can't discharge. And obviously, we're not doing the discharge portion of it, we're just doing pump control. So don't have to worry about that. And if you go and check our manual, there's another code in there, and that just basically says that you can't go and discharge polluted water. Shouldn't have polluted water in your ground sump, so that doesn't pertain to us either.
Up on the screen right now, this is the wiring schematic that we actually designed in CAD for the auxiliary sump pump system. This is just showing all of the power routing for our mechanical and electrical type devices. This does not include any of the I/O from our microcontroller or anything like that. But as you can see on our top rail, that was designated as our power rail. So up there we would find the 12-volt power supply. We used many terminal blocks, and those terminal blocks were acting as kind of like bus bars almost. And on the very end of the rail there, you see those two big blocks, and those are circuit breakers. So we have one DC type circuit breaker and one AC type circuit breaker on the top. On the second rail, that is our relay rail, and those electromechanical relays, Jim will actually talk about in upcoming slides, but those were basically just in charge of turning on pumps and lights in our enclosure. And then as you can see on the sides of the schematics, where all of our wires are going to. So our pump sockets are on the right side here, and then on the left side will be all of our lights and our battery OK and 120 OK. This is a mechanical drawing of our backplate and front panel schematics. As I said earlier, the front panel has several indicator lights mounted on the surface of it, and as you can see right there, those are the lights at the very top with the tags. There are 6 lights on the top and 5 on the bottom. The top would be all of our fault lights, and then on the bottom would be our running and OK lights. Towards the center of the face of the panel would be the LCD, so that holds our menu options. So as you can see, there's a fault clear option. If you hit the star character, it will allow you to clear the fault lights. If you hit the pound sign, it would be to set a custom sump depth for our ultrasonic sensor to monitor for. And then actually on the very bottom of the LCD, that bar, that is a active water monitoring bar. So if the user looks at it, they actually can tell how much water is in the sump. We know that it would be very easy to tell by looking at it on our prototype, but maybe in a more practical application in a home, you're not always going to be able to see down in a sump to see how much water is actually there. So we thought that was a pretty handy tool to add as well. And then right below it is our 10-digit keypad that allows the user to enter data or clear faults. And right next to it, that's our backplate. So that would be the inside of the enclosure. So that's where all of our, as I said, our circuit breakers, terminal blocks, relays, and software interfacing equipment will sit.
So we're using 2 different types of relays, 3 actually in our project. To your right here, you can see our low voltage relay bank. Arduinos are great at many things, but outputting high current and high voltage is not one of them. So we're using these to go and adapt the 5-volt output from the Arduino up to 12 volts for our control relays over here. And this relay bank, the first 2 over there are 120-volt relays. Those are essentially making sure that your wall power is good. We're also using one of those as a transfer switch to ensure that the battery is completely isolated from the system when 120 is supplied. We can do that because we have a 12-volt power supply inside the cabinet as well. The following 3 control relays are for the actual pumps and the pump run lights. And then the last one is for a battery check. That when the battery's connected, that's essentially pulled in, and it gives us a bit to the Arduino that says, yes, you have battery, and it also ensures that the fault lights are behaving correctly.
Some of the design and the physics behind the battery bank, I'll kind of keep this brief. It was actually a very involved process to do that, but there were a lot of exterior variables that definitely played a role in sizing the battery bank, 2 of them being temperature and environment. Right now, with the amount of batteries that we have, if we set our enclosure to run the pumps consistently without ever turning them off, we would have about 37.5 hours of auxiliary runtime. But we don't have them running so they never turn off. We have them running so that they cycle in timed intervals. And right now, with the way we have them cycling, we have closer to 84.7 hours of auxiliary runtime. We also had several other aspects of this project that maybe were not so much electrical. Jim actually put together a pretty nice plumbing system on our cart that you guys can all see after the presentation. And that's basically just there to move water from one holding tank to another and demonstrate the use of the sump pumps being turned on and off. And finally, we actually ended up implementing the use of a still well. During our testing period, we found that ultrasonic sensors do not take readings very well while the water is very turbulent. And so by implementing the use of a still well, we were actually able to have the water rise and fall at a more steady rate, and it was able to take more accurate readings.
So for some of the planning and the design of the software, you can attempt to see some of the green marker on the whiteboards. On the left, we have the Arduino mockup, which is showing a pinout of the Arduino itself with all of the I/O and pumps and such it is connected to, as well as where each of the wires and ports are labeled as. In the center, we have a more text-based pinout layout, so we could quickly reference it and read it for when we were actively wiring our enclosure. And then on the left, we have a variety of things. We have on the one side of the picture, we have a layout of what each of the pumps will turn on at. We have in the center, we have a brief mock-up drawing of how we were going to calibrate the ultrasonic sensor for our test bin. And then finally, we have the internal schematic of how the keypad is built and wired up. So here is the layout and pinout of the Arduino. So you can see at the top we have the keypad digits, followed by the ultrasonic sensor, and then you have the SDA and SCL, which is how the LCD itself communicates with the Arduino. Followed by that, we have our battery OK, or 12 volt and 120 volt OK bits, which allows us to know whether or not our different power sources are working correctly. Finally, we have our pumps and our fault pump lights, which will indicate whether or not something is working correctly or not. So we had a total of 13 variations of the code, and we ended up using the 12.5 variation as that had the most bug fixes as well as the most working features within it. And then for the ultrasonic sensor, we ended up using the Stillwell to help reinforce accurate measurements.
So in terms of testing, first I'll go back and explain a little bit of what this chart's saying. So when we have 120 volt power, there is a DC power supply in there. So you can run the DC pump without using the battery. So that's why you have NA over here. But in terms of current measurements, this is gonna go and just say how much power you're using. How much does it affect your bill, essentially? When AC pump 1 is running, we're pulling 2.2 amps. When pump 2 is running, we're pulling 1.8 amps. These are 120 volt pumps, so they're not going to run off the 12 volt system. But the DC pump, which is a 12 volt, off the AC power supply, it pulls 1 amp. Off the battery, it pulls 5.75 amps. And then in standby power, when it's plugged into the wall, it only pulls 1 milliamp. And standby power is running the LCD screen, a couple of relays, and then the Arduino. And then on battery, standby is pulling 2.9 or 290 milliamps.
So is this product applicable and practical? Yes. All you have to do is mount the cabinet to your wall and find a place for your pumps and your batteries, as the cart and plumbing we have is purely for testing and demo purposes, so people can see how it works. It is most definitely applicable towards the homeowners, as It is as simple as screwing it into your wall, and it should work on its own, and you wouldn't have to worry about it turning on or off. So for the total cost of this project, we originally anticipated a cost of about $1,500 to $1,600. However, after needing replacement parts and things breaking, we ended up needing to pay a little over $2,000 in total cost. And then the efficiency of this product is almost entirely based on whatever pumps you have hooked up to it, as we have our pumps at lowest of 25 gallons per minute, and it can scale upwards to however fast your pumps can push the water.
So now we're going to talk about some of the lessons that we learned about designing and building this process. The first one would be protection devices. We didn't actually learn any lessons from protection devices, but our protection devices definitely did save us when we needed them to, so we did think it was still notable to talk about them. That would just be our circuit breakers. During our testing, we did have a couple instances where wires got crossed, we turned the power on, and the breakers did save us from destroying equipment. Paying attention to wiring. This one was definitely the biggest lesson that we learned of all. This actually cost us multiple pieces of equipment because we did not pay attention to what rails we were hooking power wires up to, and it did ended up having to replace several pieces of equipment. Which actually brings me to the next lesson of ordering multiple replacement parts and having them on hand prior to the testing period. We lost a lot of time during our testing period from waiting for new parts to come in, and that really did hurt us towards the end and caused us to have to be here a lot later and a lot more than we really wanted to or should have needed to be. And then last but not least would be the software development. The software actually panned out pretty good, but if we had to do it over again, knowing what we know now, we definitely would test the software and implement it piece by piece instead of waiting until the very end to test it all at once. That also really hurt us during the testing period.
So we wanted to acknowledge a few people, such as some of the professors that helped us along the way, whether that be through feedback and advice, helping us build things, or just helping us get supplies and components for our project, being Deanna Pazega, Glenn Raitt, Seth Norberg, and Michael Rudisil, as well as Caleb Polkinghorn. Finally, I would like to thank Bryson Zimmerman for helping me finish with the programming, as without him, it is questionable whether or not we would have enough of the programming working correctly for this presentation.
We have time for one quick question. And if the other team wants to start heading up there.
So maybe you mentioned it, maybe I missed it, but what's the competition for you guys out there? I know a lot of homeowners do like 2 sub pumps, but in this case, that wouldn't help you if you lost power to your house.
So our control system is actually a prototype or a one of a kind at this time. So right now there is no product market for this product right now.
Please do stick around and watch it work. I was promised a video. I don't know what happened there, but it does work. It's pretty impressive. It's fun to watch. So please do check it out afterwards. And now we have Caleb and Alex. Stay at the podium. Why are you taking it out of there? And put the cover on.
I know. I thought it was.
You're not supposed to notice this.
Sorry.
You good?
We're good. I think I got it.
Okay.
So I'm Caleb Murphy,
I'm Alex Rodenberg.
and our senior project was a single axle scale. A little bit of background. I'll give this to Alex.
So for our customer requirements, we're building for Steema Dairy out of Posen, Michigan. And our problem statement was to develop a means of weighing wheeled vehicles to ensure they are under state weight limit laws while being easy to use, durable, and reasonably accurate. Our customers' requirements were to have an effective range of between 14 to 22,000 pounds, just to make sure they could encompass the weight of
a single axle of a semi-truck. They wanted an accuracy of plus or minus about 500 pounds, which can be anywhere from about 2 to 4%, using that effective weight of 14 to 22,000 pounds. They had a budget of $3,000. They wanted it to be robust since it will be used on a dairy farm in northern Michigan, and it will be exposed to elements and obviously having large vehicles driving over it. And they wanted it to be easy to use.
So this is an image of or two renderings of our project. In the upper image here, this is the concrete pit and the scales placed inside of that, and it kind of gives you an idea of how the vehicle would travel over the scale. And then the bottom image is a rendering of a cutaway view, so you can kind of see how the scales fit into the concrete pit there.
This is the preliminary wiring diagram from our first semester of the design. So on the left in figure 3, you can see the sending unit, as I call it, which is going to be housed inside the scale in that concrete housing. And that'll be responsible for receiving the data from the load cells and sending that to the receiving unit, which can be seen in figure 4, which will display all of that information to the user and give them an ability to interact with the scale.
So now we're going to go on to the build of this project. So we're going to start off with the mechanical side. This is the frame. So this frame is constructed out of 2x2 quarter-inch wall steel tubing. It needed to be rigid because if it wasn't, then we wouldn't be able to get accurate readings of the weight of the vehicle. It is what all of the other parts of the scale are built onto. And then the overall dimensions of this are 36 by 18. And then in this image here, you can see on the 4 corners there are 3/8 plates. This is the location where the load cells will be placed. Then for this one, this is some of the fabrication that we had to do. We had to use the lathe to turn down the guide pins to help center the pressure plate. In the middle image, you can see the frame next to the pressure plate. And then here's welding the mounts for the load cells onto the frame. Within the welding the frame and stuff like that, we had to do weld sequencing and use jigs to help keep that frame square and mitigate the heat distortion on the frame. And so this is the mechanical assembly. So here on the upper image, we have one of the banks of the scale, and on the top you can see that that's our pressure plate. That is 3/8 inch AR 500 steel. It was donated to us by Allied Mechanical Services. Then below that are the guide pins, as you can see in this rendering here. The guide pins are located onto the load cells by studs. The studs are bolted to the frame and then the frame. For each bank, we have the pressure plate, the frame, 4 guide pins, 4 load cells. They are 3,000 capacity S-type load cells. 4 grade 8 half 20 bolts. We are constrained to the half 20 because of the load cells, and then 4 grade 8 half 20 studs.
So here's that electrical sending unit that I was talking about, which is housed within the scale itself once it would be completed with the concrete form. The main brains of this operation is the Arduino Mega here, which you can see at the top of this image. There are 8 amplifiers which are needed to receive the data from the load cells and give that to the Arduino in a format that the Arduino understands. And we can see those in the soldered into printed circuit boards right here in the middle. Then we have a Bluetooth module which allows it to communicate wirelessly with the receiving unit, which will be discussed in a moment here. And that you can see on the side here. This system is powered by 120 from your wall outlet, and that gets brought into this box through 120 volt AC to a 5 volt DC converter, which is down in the corner, which then goes up through a DC to DC booster to bring that 5 volts up to about 9 to power the Arduino. The load cells are connected to turn blocks, which are soldered into printed circuit boards down on the bottom here, which then get connected through the amplifiers and connect to the Arduino. After this got completed, prior to working on the receiving unit, we did calibrations with the load cells, and we did 2 load cells individually or with each other. So we did 4 calibration tests, and this was essentially because we were planning on making an ability to tell the user whether they were off-center on the scale or not. We ended up not being able to implement that due to a lack of time. This is the receiving unit. This, again, the brains of that, this portion of the system is another Arduino Mega. And the next-gen display, which you can see here, is what allows the user to see the weight that is currently on the scale, as well as to interact with that scale. And it receives that through the Bluetooth module over here from the sending unit, which we previously discussed. This is powered by AAA batteries, which then goes through another DC to DC booster to give that Arduino, as well as the next-gen display, the proper voltage to function. And if you see down here the different displays that the user could be seeing, on the left in figure 16, that's what they will see upon startup. And once they press start, it'll start displaying the current weight of on the scale. And in order to follow weight laws, they need to know different axle weights, so they can select which axle they are currently weighing, either steer, drive, or trailer, and they can select these as many number of times as they need to. And once they press finish, it'll bring them to this second screen over here, figure 17, and that'll display the total of each individual axle type as well as the gross. Here's just a snippet of the code. This is not everything, it's just the highlights from each one. On the left, you can see the sending unit code. On the top, this is where we receive the data from the load cells to the Arduino. That's where we add the received values, and this gives us a total, which is what ends up getting sent to the receiving module. In the receiving module, when you press the start button, it clears all the text on the display, and then it'll display ready to indicate to the user that is ready to start weighing. This is what displays the total weight, or that's what receives the total weight rather, and this is where it displays the total weight. And here is just an example of how those steer, drive, and trailer buttons work. When you press it, it tells the user to wait, and then it stores that value, and if you press it again, it'll add to that value to be displayed after pressing finish.
So now is on to the concrete portion of our design. We were unfortunately not able to complete this portion due to the extended winter and time constraints. So the concrete portion, we call it a footer and pit. It's what houses the scales. It would be recessed into the ground, so that way when the user drives over the scale, he doesn't have to drive up or down. The pressure plates would be at ground level, and he can just drive fluidly over. The concrete that we would be using would be 6,000 PSI high-strength concrete that would be reinforced with half-inch rebar. We also designed for an open drain in the center of the pit, so that way if it rains, any water that could collect in there would drain out. It would be a 2-stage pour, so first the hole would be dug, and then the lower left image is essentially the outer form that would be built, and then the footer, the bottom part of the pit would be poured, and then the inner form would be placed, and then the walls would be poured. The inside dimension of the wall is kind of important, because that way if the driver were to suddenly stop or accelerate on the pressure plate, it would help mitigate any shear within that would happen within the load cells. So, yeah.
Cost. So our budget, as stated previously, was $3,000 from Steam Dairy. Our build cost for what we actually built, as you can see over to your right, It cost us $2,239, and that is without the concrete being poured and everything fully ready for use. We did make an estimate for them so that if they did pour the concrete, it would cost them about $2,557 just in materials to build the scale, which does come in under budget. Testing. So our first test we did was over at the PEEF. They allowed us to go over there and use their 45-pound weights and test the accuracy of our scale. So we put 5 45-pound plates on each bank of load cells. So that was a total of 450 pounds. And we read 454 pounds when that 450 was on there, which gives us about a 0.8% error, which is well below what we were expecting in the design and build of this whole thing. The limitation we ran into with testing is since we didn't get to pour concrete and actually drive a vehicle over it, we could not test out the range that they wanted, so that 14 to 22,000 pounds, we were unable to test that.
So this is another test that was conducted. Pettibone was gracious enough to allow us to use their high rail axle as for a test. Like previously stated, they had a theoretical weight of 2,000 pounds of the axle. Once it was placed on our scales, our scale read 2,007 pounds. This was within 0.35% error. To mitigate any risks with this test, because the axle could roll, we had Kale load the axle onto the scale, and we all stood a distance back, and yeah.
So our final product, as you can see here, this is what it ended up looking like. And those are what the user interface ends up being. So the requirements in comparison to what we ended up with, we were unable to test the effective range as previously stated during testing. Our accuracy, assuming the 45-pound plates were well within tolerance, we were well under our 2 to 4% error that we promised the customer. Our budget, we did come in under budget, again, with just material costs, that is not including labor. And ease of use, the user interface is simple and easy to understand for the user.
So for our business case, what makes this better than what's on the market right now? So for single axle scales on the market right now, for the price, they don't have the Bluetooth capability with the handheld device. This allows the user to be able to read the weight in the truck, whereas the other ones at this price, you would have to get out of the truck and go and check the weight manually. Also, with our design, there are very few specialty parts. There were only 8 total machine parts, but it's one part, and then it's easy to repair. And at this time, we would like to thank Steema Dairy for allowing us to build this scale for them. We would also like to thank the professors in the engineering department for helping us along the way. We would like to thank NMU Welding Facility for helping me brush up on my welding. Allied Mechanical Services for donating the steel. Pettibone for allowing us to use their axle. And then Colin and Jackson, they were very essential in the last couple days.
Any questions?
Kurt Tucker. Wonderful presentation and a very interesting project that you worked on. Question though, to test out your scales, did you give it some thought about using the tension compression machines in the department? Because they would give you right down to, I mean, the fraction of a weight.
Yeah. So we did end up using the Instron unit. Is that what it's called? Yeah. For calibration, but we were unable to use it for testing just because of the size of our the plates. They wouldn't end up fitting in any machine that we have here.
Oh, really?
That would
Even
provide
in
an accurate value for us.
Okay. So Then the other one is the electronics. How I might have missed it, but how did you seal those? Were they hermetically sealed so that none of the environment would bother them?
Yeah, so there's, for each of the load cell cables, there's little plastic connectors that are weather tight, and then same for the 120 power coming in, and they're all inside of a plastic weatherproof box.
Afterwards, you can see the box right between the two scales.
And we forgot our handheld device, but we'll run over and grab that and bring it in too.
Good. Other questions? No, that's how they first tested it. Any more questions? Lessons learned. I'll ask one. Any lessons learned, gentlemen?
Yeah, like you said earlier, the don't delay. A setback in the beginning was gathering materials that set us back, and then we also had we struggled with the distribution of labor. So all of the mechanical end was done by me, and it took a total of estimated 24 hours or so for the machining, and a little bit more of that, touching up on welding and stuff like that. So yeah, it was that struggled.
Oh, okay. We're not done. We're not done. We got another question. Couple minutes. All right.
Did you guys get a chance to like lay out your concrete, like your rebar or any of the molds or anything?
We didn't get a chance to do that, no.
Shame.
Yeah.
So for an off-center load, do you know how much the variance would be if you were all the way to the left?
No, I was planning on using just percentage of which. So if you look at the scales to your right there, as you're driving onto it, there's 2 load cells on either side of each bank. So I was going to do a percentage of the total on that bank. So if it's over a certain percentage on 2 versus the other, it would say that it was off-center.
While I'm walking, there's seating available in the front if you want to move up to the front. We also have more chairs if you want to pull down some chairs as well.
You guys mentioned putting a drain in the bottom of the concrete, so if you have to pitch that towards the center, would that little bit of pitch affect the load cell as far as how it's going to read?
It shouldn't because we designed for adjustment within the load cell. So yeah.
And one last question. Could you give some lessons learned on team dynamics?
I'll let you take that.
Pick group members that you're willing to spend a lot of time with. And if you have a source of income for a project, make sure every group member has contact with them as opposed to one.
There's some inside information there, but well done. It came together. So good job. All right.
Thank you.
All right, our penultimate group is Leaf, Diego, and Shad. And they've got the pretty cool hitch-mounted bike carrier there. So they'll talk about that. This is another one from scratch. They learned a lot of good lessons as well. We ready?
Yes, sir.
All right, go for it.
All right, first I'd like to thank you all for being here. My name is Chad Wolk,
I'm Diego Romero. And I'm Leif Gustafson.
and this is our Easy Lift bike rack. To begin, I'll give you guys some problem background. We discussed the need for easy bike transportation. Bike transportation often requires car-mounted racks, but existing bike racks require users to lift the weight of their bike and often obstruct the trunk. This design focuses on creating a bike rack that is easy to load while keeping the trunk accessible. Our motivation for this project was based on user experience. We wanted to reduce the strain of lifting a bike's full weight, and it would make longer bike transportation easier, especially for heavier bike models or riders with physical limitations. Our problem statement is to create a bike rack that allows to be easily loaded and unloaded onto a car with minimal effort and allows easy access to the trunk.
So our design process involved a comparison between the functions that we wanted and the methods to get those. So we wanted to carry the bikes. We could do that by holding onto the wheels of the bike, or we could put metal rods through the frame of the bike. For trunk access, we could have it sliding away from the trunk. We could have it swinging to the side, or we could have an arm pivoting away from it. For the easy lifting, it could be a ramp up to the level, or there could be a crank with a high enough gear reduction that it's low effort, or we could just use an electric winch. Our target specifications were that it should support at least 50 pounds of weight. The bikes should stay within 3.5 feet of the back of the vehicle, and the assembly should weigh around 30 pounds or less. We also needed clearance of at least 1 foot off the ground at all times. Our selected design used metal rods through the frame as well as some wheel holders near the back. We used the pivoting arm method that would swing away from the back of the car, and it would be raised using a battery-powered electric winch. Here we have an image showing it in the horizontal lowered position and in the vertical loaded position. To interface with a car, the square tubing mount would fit into a standard 2-inch hitch receiver on the car. To interface with the bike, the rear wheel would fit into the loop of a wheel holder, and 2 frame carrying rods would fit through the frame of the bike.
Here's the design overview. We have a lot of different components and we use some terminology here. So going from the top to the bottom, we have the mount, and that attaches to the vehicle's hitch. We have the battery, which powers the winch, which raises and lowers the cable or the carriage arm. We have the cable arm, which raises the cable to create leverage for elevating the carriage. Wheel holders, which stabilize the rear bike tire. We have the carriage arm, which is the main pivoting structure. The carrying rods, which support the bike's frame, and then carrying rods are used to, or frame straps are used to attach the bike frame. And here is a list of the different sub-assemblies, which in later slides we'll talk about how we tested them. But we have the cable arm sub-assembly, battery and winch, the mount and the base, the wheel holders, and as well as the carriage.
The step considerations. Making bike transportation accessible to everybody is a very nice, a good thing to think about. And we, keeping components simple. I'll restart. Making bike transportation easy for everybody is a very appealing thing for us. And we thought if we kept these components very simple, it would be easy to maintain and allow for a longer lifespan of the bikes. We decided to make the assembly out of aluminum. We chose to do this because of its low corrosion resistance and its low weight. We chose to make the base and the mount out of steel because of its strength, and you must clean it regularly to avoid corrosion.
So here's our bill of materials on the left here. It's divided into 4 different categories. We have hardware, steel stock, aluminum stock, and other. The final cost of this was $438.94. We did get quite a few materials for free from Dr. Kale or other students here. And if we did have to buy all of that, the final cost would be around $600. The final design costed significantly less due to us switching to aluminum rather than using steel. And like I said earlier, aluminum was provided by Dr. Kale and another group.
Our project schedule, in hindsight, was very ambitious. We anticipated being able to complete one subassembly on a weekly, or in our worst case, a bi-weekly basis. In reality, scheduling conflicts and changes in the design meant that our final schedule was about 2 weeks behind what we expected. For fabrication, we cut our stock using a bandsaw and turned, surfaced, and drilled our parts using manual milling. TIG welding was used on the base and the mount, the carriage, and the wheel holders. And to get the bent radius for the wheel holders, we used a bench vise with a metal die. It was a bit of a jury rig, but we did get the radius that we wanted. For this fabrication, we followed general OSHA guidelines on workshop safety and machine handling. So all fabrication required at least 2 people present. All subassembly testing required at least 2 project team members present to observe the subassemblies being tested. And we all required safety glasses and appropriate footwear when handling machinery, which also included the assemblies themselves.
The base and mount. We chose to make the base and mount out of A36 square tubing. The mount is 31 inches long to account for the length inside of the hitch receiver, the battery and winch, the cable arm, and clearance for the bikes to not hit the vehicle. The base is 7 inches tall, and there is a cut at the top to allow for the carriage to sit at an angle. And then there's also a chamfered side on the mount side to allow for clearance for the carriage to swing up. And the test for the mount and base, we started off with the mount test where we just inserted it into a 2-inch hitch. And then we tested the integrity of the weld by putting the mount into a vise and then putting a 50-pound load inside of a crate on top of the base. And then after this, we would check the weld and see if there was any cracks, and we found no cracks. The results, the square tubing fit into the hitch receiver, the weld did not crack, and the square tubing did not bend.
So another component is our carriage. The carriage holds the bikes using carrying rods and wheel holders. This part is made from 62 inches of aluminum U-channel and weighs about 9 pounds. It has 3 features, which are these adjustment holes. These holes are for adjusting the location of the wheel holders. We have the tether plate, which is made for attaching the winch's cable, and then carrying rods are welded in place and support the weight of the bike and attach to the bike's frame.
We ran calculations for the U-channel to make sure it could actually support the weight. We did some calculations for buckling when it's vertical and also bending when it's horizontal. And the forces we found were within acceptable ranges. So we decided that the component would not fail in use. We had the pivot point to pivot the carriage about the base. This used a 1-inch diameter steel clevis pin. And then when fully raised, the back of that U-channel for the carriage would contact the base to prevent any further rotation. A locking pin would work in combination with tension from the winch's cable to keep the carriage arms stable in the vertical position during transit. To test the pivot, we installed the carriage on the base with the clevis pin and freely rotated it to make sure there was clearance. During this test, we found that holes for the locking pin were slightly misaligned, so those were widened to allow alignment. And we also found that there was a need for cushioning between the base and the carriage. So we accomplished that using contact cement with elastomer padding.
The carrying rods. The carrying rods are made of 2 20-inch long aluminum rods with a 1-inch diameter. They are welded to the carriage, and each carrying rod has a strap around it to securely attach the frame of the bikes to the rods. Testing the carrying.
For testing the carrying rods, the spacing of the carrying rods was checked to ensure compatibility with different bike frames. The final spacing in between them is 18 inches, which fits 3 different size bikes. The result is that the size of the bikes, the size of the bike straps interfered with loading during our initial tests. This was resolved just by adjusting the orientation of the straps about the carrying rod. And in these three pictures, we have three different sized bikes, and as you can see in each one, the location of the carrying straps on the bike's frame is different in each one, but they all worked well.
The battery and winch. The electric winch allows for the bike rack to be lifted with very little to no human effort. The Badlands 2000 Marine electric winch was selected because of its low cost, its high carrying capability, and its remote control. The Mighty Max battery was specifically selected just for the winch, and it sits inside of the battery box with those specifications. The winch weighs 15 pounds with the battery weighing 13 pounds. We tested the performance of the winch by strapping it on, clamping it onto the work table and then attaching a 50-pound load at the bottom and then raising the load and then holding it there for about a minute and then bringing it down. We did this 10 times and saw no failure with the battery. The result, the winch cable did not slip and the battery did not lose charge, but we did test this extensively running the winch.
So for the actual route of the winch cable, we needed to elevate it to get the right leverage. So we used aluminum arms supporting a 1/2-inch rod, which itself supported a pulley, which routed the cable to the correct height. 4 shaft collars secured this rod in place, and each of the pair of arms was bolted together on either side for added rigidity. The 2 arms on the mount can be removed with a removable pin to allow the full subassembly to swing out of the way if that is an obstruction to opening the trunk of a car or for storage. For testing the cable arm, we installed it on the base and the mount, installed the winch, routed the cable over the top of the pulley arm and down to a 50-pound weight on the ground. Then we operated the winch, lifted that weight off the ground, and checked for any signs of buckling, bending, cracking, or otherwise failure in the cable arms when they're under tension. The result, we did not observe any signs of failure in any of the 4 cable arms. The wheel holders keep the rear tire of the bike stable and allow for some extra support. The location of the wheel holders can be adjusted using the bolt holes on the side of the carriage. And the loops are made of 1/2-inch aluminum rods welded to a 1 1/3 inch aluminum tube, and then that is welded to a 3/8 aluminum plate. The loops are 11 inches long and interface with most bike-sized frames. The total weight is 2.7 pounds. To test the wheel holders, we had to, the size and location of the wheel holders should allow multiple bike sizes to fit while on the carrying rods. Testing was done to ensure that at least 3 different sized tires engaged to a depth of 1 inch into the loop. A hybrid fat tire and mountain bike were used for these tests. Result, the wheel holders held 1 inch of both tires' size while the bikes were held by the carrying rods.
For the full assembly test indoors, the mount was secured to a workbench and all components were installed. A series of tests were done, starting with no load, like in this picture shown here, and then followed by a 50-pound weight, which is our milk crate filled with steel. And then we did 1 bike and then 2 bikes. The result was that all components upheld structural integrity and worked as intended in this static situation. Lifting and supporting 2 bicycles in the vertical position all worked well.
Following all of the subassembly tests, the final test was an outdoor test mounted to the back of a truck. This was conducted in the Jacobetti roundabout here. We began first tests unloaded, incrementing at speeds starting at 5 all the way up to 25. After the unloaded test passed, we did it with 1 bike loaded. Once that was passed, we did it with 2 bikes loaded. And we found that easy lifting bike rack assembly could easily support 2 bikes in the vertical position at 25 miles an hour.
So for project status, the construction of the easy lifting bike rack is complete. All of the sub-assemblies have passed testing and the full assembly completed outdoor testing. The final weight of the rack is 38 pounds, but then when you add in the battery and the winch, it's about 70 pounds. Our initial goal was 30 pounds, which we are over by quite a bit, but the bike from the distance to the car is 17 inches, which is well within our range.
Market comparison. So in the market, these are some options that we went over and we decided to compare our model to last semester, but the market ranges from about $43 to all the way up to $900. These designs allow trunk access by either pivoting or being pulled out to allow trunk access. With the higher quality ones, as you'll see in this picture, having a hydraulic press, which you just pull on and it'll slowly bring the assembly down. The potential price we're looking at if we were to sell our bike rack would be $700 before the cost of labor.
We had a lot of lessons learned throughout our year doing this. The project's schedule was significantly delayed by redesigning the carriage, which reinforced the importance of getting input early on. Also, interdependencies between components impacted work on multiple sub-assemblies, especially the wheel holders and carriage. We found that we would need one certain sub-assembly before we could move on to the next, and that caused us delays.
We also did most of our early calculations exclusively using finite element analysis rather than hand calculations, but this ended up producing errors further down the line that we had to recalculate later. So while the computational methods were useful, they are not sufficient on their own.
The assembly could be improved by optimizing the pulley system for faster access and easier repair. This would significantly enhance the overall convenience and reliability of the easy lifting bike rack assembly.
I'd like to acknowledge specifically Professor Norberg and Dr. Kale for helping us throughout this thing, but as well as all of the NMU faculty and staff. And we'd like to thank Eric's group for giving us some aluminum tubing. That's the end of our presentation. At this point, we'd like to open it up to any quick questions.
Lots of questions. Saw the back first.
So for your speed, you chose 25 miles per hour. Obviously, we'd probably want to do faster than that, but you're limited to probably,
Yeah, we were limited to just going around Jacobetti Center.
Right, I understand that. Did you guys ever consider any sort of wind resistance and what sort of stress that would cause on your actual assembly?
We did not know.
Okay.
You guys had mentioned that you started with one bike and then moved up to 2. Do you think that it'd be more stresses would be found actually on your design if there was only one bike on there due to balancing reasons?
Yeah, we thought that initially, but we found that even with just one bike on it going around at 25 miles an hour, we didn't see any like leaning or anything of such like that.
So my question is about how far it sticks out from the rear of the vehicle. There is laws in place that require a flag to be present on anything that sticks out over, I believe, 2.5 feet. Do you have any design intent to accommodate that?
When we were doing research, we saw that it was 4 feet that you would need a red flag to be sticking out, and ours is under that.
Oh, perfect. My information was wrong then.
Yeah.
So you guys mentioned that you've designed this to hold 50 pounds of weight. Where did you gather that was
Just like 2 typical bikes.
Okay, and you said you ran FEA on that as well?
Yes, sir.
Do you remember what your factor of safety was on that?
Offhand, I recall it was very close, which is why we began questioning our FEAs. I want to say we set it at 3, and we were getting about 3.5. That was when we started doubting things.
Thank you.
All right, it's actually time to move on to the next, but again, in about 20 minutes, we'll all be done, and feel free to hit them up at their displays. Can we get a round of applause? right. Now we have our last group, Seth, Alex, and Caden. They are doing a project sponsored by Able, and it's been a very nice partnership, and I'm looking forward to seeing what you all came up with. All right, so on you.
All right, my name's Alex Carpenter,
I'm Seth Hornick. I'm Caden Clausen.
and today we'll be presenting Project Falcon. So some background on the project. Able came to us and asked us to redesign a device that works with their existing implant system. The implant is an inline cerclage wire system for treating periprosthetic fractures, which is essentially when you have a total hip replacement, that artificial hip creates pretty much unnatural forces in your femur, and that can lead to fractures. So currently, this is the device they have. As you can see on the right, there's an exploded view. There's over 55 different components, and many of these components are machined. On the left is the device together. So the issue was it was just very expensive and complex, and the manufacturing proved to be difficult. And they want a sterile pack device as well. So with this device, you would have to take it apart after each operation and sterilize it, and that can kind of run into the problem if the sterilization wasn't done good. You can have cross-contamination and risk infection in your next patient. So we've got a quick video kind of the insides of our product. You'll see an exploded view of how everything goes together and what the insides look like. A few things to note: the top knob in the gray is our collet tension knob. When you turn that, you're basically compressing a collet, which clamps around the cable. The blue knob is our tensioning knob, which turns a Acme screw internally. That results in a direct linear motion. So there is no twisting the cable, which is something we wanted to avoid. And then to set the final set screw on the implant, you just turn the entire device as if it's a screwdriver. So we'll kind of zoom in and see an exploded view of what's going on the insides. One thing to note is once this device is assembled, those snap clips, they keep everything together, so there's not much risk of it coming apart in the operating room. And as you can see, it's only 6 components compared to the over 50 components of the previous device, and only 2 of these parts would need to be machined by a Swiss machine. So a big thing that we dove into before we started any further development or design. When we initially sat down, the previous device had a docking mechanism for the implant. Since we were tasked with making this single-use in plastic, we figured it'd be very hard to come up with a way to dock onto that implant and keep it strong enough to resist the forces. So kind of sat down and actually figured out what was going on with the implant, and we made the hypothesis of as you tension that cable, it's actually going to pull the implant down into the bone, which would then want to resist the torsional forces when you torque down that set screw in the implant. We did multiple tests on different materials. You're seeing a turkey bone there. We only observed the witness mark in the middle when it was a misuse case, meaning there was no tension applied to the cable at all. So that'd be an error of the surgeon, but it is still a possibility. And then here are our results from that test. We tested on a model femur bone, which kind of it's a lot softer than normal bone. We tested on Delrin, which we found to have similar properties to bone. And then we tested on a turkey leg just to kind of get a more real world simulation. And all of these tests, the implant did not flip over, and we only observed witness marks when it was a misuse case. So some fabrication and assembly highlights. We worked closely with Able's production team to manufacture the cannulated driver tip in-house. So we got them the drawings for that sent over, and they did a great job with it. They're very quick. They got us 5 different components so we could test them and heat treat them. Everything was within spec. The tolerances were great. Some of the equipment we used were the Swiss turn machines. Those were used to manufacture the cannulated driver tip, like I said, as well as the collet. We use the resin and FDM printers here at Northern to prototype the plastic components because injection molding wouldn't be cost effective when you're prototyping something. And we use manual lathes for creating much of our fixturing, as well as creating threads. We found that when you try to 3D print threads, you often don't get the results you want, so we manually machined in all of our threads. And we also used wire EDM for fixturing components and a furnace for heat treating.
Then on to the design process, risks, and standards. So some of the engineering tools that we used are software. So into SolidWorks, that is a CAD program that creates the models for your parts, and then that can be used in CAM to help with G-code for manufacturing the parts. Then we have Preform and Bamboo Labs. Those are both 3D printing softwares that we used. Then into manufacturing, like Alex said, we use the Swiss turn lathe, manual lathe, wire EDM, the resin and FDM 3D printers, and the furnace for heat treating. We also had some testing equipment, the MTS, that is an electromechanical test system at Able, the Mark 10, which is a torque gauge, also at Able, and then the HRC tester, which was here at Northern. Some risk prevention that we did. We wore safety glasses, worked in pairs, we used gloves for the heat treating, and then we also used common sense. So material is really important for this. Being a medical device, we need it to be sterile and biocompatible with the body. So we chose to use stainless steel 17-4H900. This is a good, strong material. Then we used aluminum 6061 T6. This has a high coefficient of friction, which is good for holding onto the cable for the clamping mechanism. And then ABS that was used for the parts that need to be injection molded. And ABS is also good because you can sterilize it using gamma rays. Then into our material costs, we use stainless steel 17-4 for the cannulated driver tip. That came out to $7.19. And then the aluminum 6061 T6, that was used for the collet, and that came out to 39 cents. And then 2000 Tough was the resin that we used for the 3D printing. That emulated the ABS because it has similar properties. And that came out to $38.60. So the total cost for our material was $46.18. Then into the part goals and procedure. So we had 3 parts that we were mostly worried about: the driver tip, the Acme thread, and the collet and collet knob interface. For the driver tip, we wanted to apply 30 inch-pounds of torque. This was to achieve the proper set screw torque without shearing the cannulated driver tip. Then the Acme thread, this needed to withstand 100 pounds of force of compression. This was to apply the proper compression force without damaging the thread. And then the collet and collet knob interface, this was the needed requirement of 100 pounds of force in tension to apply the proper clamping force to the collet without the cable slipping. And then on the right, we have an example of one of our procedures that we had. This was for the cannulated driver tip. We made these before doing the actual testing. Then into a FEA on the cannulated driver tip. This is used in SolidWorks. So in figure 2.1, you can kind of see how the analysis started. We fixed the portion of the threads and applied a 30-inch-pound torque to the cannulated driver tip. Then in figure 2.2, you can see the von Mises stresses, blue being the lowest, red being the highest. So you can see that the most amount of stress was seen at the cannulated driver tip, which is expected. Then into figure 2.3 and 2.4. In 2.3, you can see we added a factor of safety of 2 to that, and it doesn't seem like there's any spots that go outside of the factor of safety of 2, but looking up close in figure 2.4, you can see there's small points that go outside the factor of safety of 2, so this is where you would see deformation or fracture if it was to fail. And then into actual testing of the cannulated driver tip. So this is kind of simulating the FEA analysis that we just did. using SolidWorks, but this is a physical test. So we did a condition A, which was the non-heat treated, and then the condition H900, which was the heat treated portion. We set a goal of 35 inch-pounds, and we achieved roughly 40 for most of these tests. All of it passed. You can also see there's the torque gauge in the top left photo, and it had a max of 50 inch-pounds, so we didn't want to go over that and break that device. And on to Caden with the heat treating.
So like Setha just mentioned, we did some heat treating to the driver tips. In the photo all the way to the left, you can see the brown driver tip, which is the heat treated one. To the right of that is a silver one, which is all raw material. And then to the right of that again is the fixture that we were using to test these driver tips in. And then to the right of that, there's two photos. We used Abel's vision system to detect if there was any deformation before and after we did the torsion test. These two pictures are on the heat-treated sample, and there was no deformation on either of them, but we also did it on the non-heat-treated version, and there was still no deformation on the raw material. All heat treating was done here on campus to condition H900. And then our next test we did was the collet and collet tensioning knob. We ran 5 tests with a goal of 100 pounds of force. The aluminum showed to be the best, which obtained a 70 pounds of force before any slippage. The way this test worked, we used the MTS machine at Able, and we had designed a fixture for the bottom to hold the collet and the collet tensioning knob, which the fixtures can be seen on that table over there. And then we used Abel's already made fixture to hold the cable, and then the MTS would just gradually apply force, pulling them apart. And then once slippage started occurring, it was recorded on a computer that is not in the picture. And then that table there to the left is just all the recorded data that we got from that computer. The next test we did was on the Acme thread. We had been concerned about when the thread goes under compression force, is it going to damage the thread profile and no longer thread properly? We ran 3 tests and had a goal of 100 pounds of force for all 3 tests. The first 2 tests went to 295 pounds of force, and the third test, we really wanted to test it, and we pushed it to 1,005 pounds of force. All 3 of them passed it, had no deformation in the thread profile. It worked just as it did before. We used the same exact MTS machine, but this time with 2 different fixtures, one on the top, one on the bottom. That can be seen there. And then the 100 pounds of force, I already said that. The 100 pounds of force was our goal that we were aiming for. And then comparing our device to Abel's current device, their device is very expensive. It's over $3,000. There's 3 different components for it: the pistol grip, the docking mechanism, as well as the torque wrench. It's inaccessible. You need to book it out in advance to use it. It's complex. There's over 55 parts to it, and it needs to be sterilized before every single use. Our device was inexpensive. The material cost was $46.18. It's compact. It's readily available, so it's on shelf, ready to be used at any moment. It's simple. There's 6 parts, and it's user-friendly with no pre-use sterilization that needs to be done. Our current project status and agenda. Currently, our product and surgical technique guide are complete, which can be seen on our table over there after our presentation. We started with preliminary testing, and then did manufacturing, then development, followed with final testing. We created a looks like, works like prototype. Our final model would be made out of ABS instead of the resin. We just used resin because it's a lot cheaper and easier. Our total project cost was $505. The collet and tensioning knob are currently not meeting our standards of 100 pounds of force, but this likely can be easily addressed with material change or a design change. And our project abstract was accepted to the IMEC-E, which is the International Mechanical Engineering Congress and Exposition. So we have some lessons learned and some future development with our conclusion. The first lesson learned was time. I'm sure everybody that made a project can agree that it took a lot more time than you were anticipating. Our second project was development. It's very easy to get caught on that first idea that you think is going to be the winner, but most times it's not. We used a fail-fast mentality, so we could learn what we could as fast as we could and apply it to our next prototype. And then with any group project, it's very important to have clear goals, be open-minded, and have great communication. So future development, if we wanted to continue pushing this product, we would need to design for injection molding, do some application testing to real-world case scenarios, and then research potential manufacturers to do the injection molding for us. We would also like to take this time to give a quick thank you to people at Able Medical, Tyler Lazinski, Rob Kinney, Logan Whitehead, Adam Wainiow, Kyle Lander, and Fran Coronin, and then also some people from the NMU faculty, Dr. Norberg, Joe Ruthier, Cale Polkinghorn, and Dr. Marler. We would like to open this time to take any questions.
How much time did you spend doing design on this project?
What do you guys think? I mean, it's hard to give a exact estimate, but I mean, just design in CAD. We'd say went through 3 different variations, so maybe an estimate of 20 hours.
We also had to make a lot of changes throughout the process. Certain things wouldn't work, so we spent a lot of time doing more changes in development in our device as well.
I seen that the turkey bone had some wear marks when you were testing. What came to my mind is it's a human bone, each bone could be different in the way of density and strength and composition, however they led their life. So how does the doctor or whomever know how far to tighten that? Because they're not going to see it. When do they know to tighten it so it doesn't over tighten and make a mark?
So that is one thing that could be improved. There are various devices on the market that either indicate the tension force you're at. There are, however, a few that also don't indicate. So it is a thing that kind of goes by feel and experience of the surgeon. They never recommend going over 100 pounds of force. So that could be one thing as well with our collet, is controlling that failure rate. So if you wanted it to fail at, say, 80 pounds of force, then we could design it so it would eventually slip and you'd never have the risk of over-tensioning it.
What kind of material changes would you guys implement to get the clamping force that you wanted out of the collet? If you have any ideas.
I don't know if it would be more of a material change. I think it would be more of a design change.
What would you change?
Well, we tried to change it a couple times. We had 5 different collets that we tried out. We couldn't quite get it. We think after using the collet multiple times that we wore out the contacts where the cable and the collet actually interface. So maybe getting more collets to work with would help.
Any more questions? All right, nice job. All right, this concludes the presentation portion. We didn't really schedule, but the students are willing to stand about their projects if you want to ask further questions or see demonstrations. Thank you very much for coming. Have a great Friday. Enjoy Marquette if you're not from here. And yeah, have a safe trip home. Thanks.